All right, I think we are in business. Let me just make sure that this is okay. All righty. So, as I was saying, what was I saying? I completely forgot. Anyway, yes. Any questions concerning the videos that I said that you should watch? Any questions? Any area of difficulty or hard to understand topics?
Professor Nicely, I had one question.
Okay, and this is Rena. Okay, yes, ma'am.
I noticed that in between steps, you round to significant figures, and in other classes, I've learned not to round till the very end. Are we going to be taken off if we have an answer that's like 0.01 or something away from yours because we don't round each step?
Okay, so yeah, that's a very good question. So firstly, let me ask you this. Do you understand the rules for rounding off?
Yes.
Okay, good. Because the rules are different when it comes to multiplication and division compared to addition and subtraction, right? Yes. Now, I do know that different people have different ways of, dealing with this issue, especially when it's a problem where multiple steps are involved. Based on what I know in terms of the proper way of doing things, is that when you're doing things stepwise, you round off at each step depending on the type of operation. Let me give you one quick example so that you understand what I'm referring to. So let's say, and this is just something I'm making up here, you're given a problem where, let's say it's 4.27 minus 3.95 divided by, let's say, I don't know, 20.94. All right, so let's say you're given this and you're asked to solve this. Well, of course, what you would do, of course, is solve the numerator part of this arrangement first, right? And as you can see, that is subtraction. Okay, so basically, the rule says when you're subtracting and or adding numbers, you round off according to the lowest number of decimal places, right? So you'll notice here that each of these numbers have 2 decimal places, right? So what that means is that whatever you work out for the numerator must have 2 decimal places. So let me do that calculation, 4.27 minus 3.95, right? So the answer I got here is 0.32, all right? Which is 2 decimal places, all right? I'm still gonna have 20.94 down here, right? So now we have to worry about dividing the 0.32 by the 20.94. And the rules for dividing is that you round off your answer to the lowest number of sig figs. In this case, the number of sig figs here is 2. And the number of decimal places here, I'm sorry, the number of sig figs here is 4, right? So what that means is that whatever you get for the answer here, you need to round it off to the lowest number of sig figs of the 2 numbers involved. So therefore, what that means is that this answer here must be rounded off to 2 sig figs. All right. So 0.32 divided by 20.94, according to my calculations, the answer becomes 0. Okay, so since it's 2 sig figs, I'd have to round this off to 0.015. And that would be the correct answer, all right? Now, in terms of the way I grade things like this, I usually don't take off much points, at most half a point. As you're going to see, for example, in the assignments that I've graded this morning, and I'm going to email it back to you, all right? The assignments, assignment number 1. So I'm going to make sure that I email it to you. I'm going to try to get it done by this evening, so that you can see how I, basically look out for things like sig figs, all right? But that's basically how you deal with sig figs when it comes to multiple step processes, where the rules for one particular step in terms of rounding off will be different for the next step. So I hope that clarifies what I expect from you guys, Rena.
I guess I'm just a little confused. Like this one made sense, but there's problems where you'll have like 0.00234, and there's a lot more than just a few significant figures in your calculations. And so if you round off right away, your answer is a little bit different than
Yeah,
if you
exactly.
round.
Right.
So
Yeah, in some, let me give you, okay, what I just showed you here is, you know, what I would expect if you have a combination of subtraction and division, all right? Now, let me give you an example where you would round off too early, and that could give you the least, well, a number that is not as precise as it should be. Suppose you're given, in fact, let me erase this all here. Let me get rid of this here. Suppose you're given, and again, this is something I'm just making up. Suppose you're given, let me see here, 2.59 multiplied by 3.004 multiplied by 1.9, all right? So let's say you're asked to multiply these three numbers. Okay, now let me tell you what would be the incorrect way of doing it. If you multiply these two first, right? Let me do this on my calculator. 2.59 times 3.004. Okay, so because you're multiplying, you would expect to round off according to the lowest number of sig figs. This is 3 sig figs, and this is 4 sig figs. All right. So based on my calculation, the answer would be 7.78. And then you'd have to multiply that by 1.9. And in this case here, whatever you get would have to be rounded off to 2 sig figs, because here you have 3 sig figs, and here you have 2 sig figs. All right. So if I were to work this out, 7.78 times 1.9, and the answer I got is 14, or actually 15. All right. So 15 would be the final answer if you were to round off when you multiply these two numbers first, and then the result of that rounded number, you multiply by 1.9, you get 15. Now, if I were to do the multiplication, if I were to enter all these numbers straight into my calculator, let's see what that would give. I don't know what it's going to give, but let's see. 2.59 times 3.004 times 1.9. All right. Now, again, turns out that this will give you, when you round off to 2 sig figs, because the 19 here, I'm sorry, the 1.9 is 2 sig figs. All right. Again, the answer when rounded off correctly would be 14. I'm sorry, 15, right? So in this particular case, and that's because I just chose some arbitrary numbers. In this particular case, it turns out that the answer would be the same in both if you take both approaches. However, this approach would be the correct one, all right? And I'm mentioning that because it is possible that in a separate type of calculation, you might get a different number here as opposed to here. And this one would be the correct one because you took the approach of multiplying right through, entering all the numbers into your calculator, and you round off at the end. And the reason why you can do that is because it's the same mathematical operation that you're doing, right? You're simply multiplying 2.59 by 3.004 by 1.9, right? So therefore you can round off after doing all that computation, all right? So in those cases where you do the multiplication here first and then round off and then you do the other one, you might get a different number, right? And there's a name given to that kind of error. They call it rounding errors, right? Where you round off too early according to the rules. If you round off too early, then you might get a number which is not as precise as it should be, all right? So that's when, so basically you don't round off too early when the operations that you're doing, the same rule would apply for multiplication and division, for example. And the same is true for addition and subtraction. If you were given 2.59 plus 3.004, I'm using the same numbers here, plus 1.9, right? According to the rules, the rule is that whatever answer you get here must be to the lowest number of decimal places. of the numbers involved in the calculation. So here you have 2 decimal places. Here you have 3 decimal places. Here you have 1 decimal place, which means that your final answer here must be rounded off to 1 decimal place. So if let me do this on my calculator, 2.59 plus 3.004 plus 1.9. Okay, so according to my calculator, when I round off to 1 decimal place, the answer I will get would be 7.5. All right. And again, that's because you're doing the same mathematical operation for which the rules will be the same. In this case, it's plus and plus. And if this was plus and minus here, it's the same thing. You round off according to the lowest number of decimal places after you have done all the operations. All right. So I hope that is make things a bit more clear to you, Ms. Rena.
Yeah, my question was if you added those 3 that you just did, and then the next step was to divide by 3.01, are we allowed to do 7.494 even though we know?
No. So, okay, so that kind of goes back to what I said before. So you do like what I just showed you here, right? Where you get a 7.5. And then if you were to divide that by, what did you say? 7.5 divided by what?
Like 3.01 or something.
3.01. Okay, so in this case now, the rule is different because now this is 2 sig figs.
Mm-hmm.
All right. And this is 3 sig figs. Oops. 3 sig figs. Right? So that means that your answer here must be rounded off to 2 sig figs. So if I were to plug those numbers into my calculator, 7.5 divided by 3.01, I got rounded off to 2 sig figs, the answer would be 2.5. All right. So you have to pay attention to the rules, right? Which basically says that if you're adding and or subtracting, you round off your answer to the lowest number of decimal places of the numbers involved in that operation. And if you're dividing and or multiplying, you round off according to the lowest number of significant figures.
Okay, sounds good. Thank you.
All right. Okay, good. All right. Any other questions before we move on? Any other questions concerning especially the videos that I said you should have been watching? Any questions? Okay, so if there are no questions, then let me get out of this. And I want to, before we move on to question number 5, if you have watched the videos, you'd see that one of the PowerPoints has this table here. I want to spend some time talking about this. All right, so last time we were here, we were introduced to the rate law for zero order reaction. And these are the relevant, well, especially these two equations are the relevant equations. This is the equation which relates the concentration to time. In some textbooks, they call this the integrated rate equation. And in this case here, the half-life is given by this equation. And let me just remind you what the half-life is. The half-life is the time taken for half of the initial concentration of the reactant to react to form products, all right? Or another way of saying it, it's the time taken for the concentration, the initial concentration of the reactant to be reduced by half, all right? So this is the equation for the half-life for a zero-order reaction. There are some other equations for the first and second order reactions. Let me just show you them briefly. You should have been introduced to them in watching the videos. So in the case of the first order reaction, this is the rate law. Rate is equal to K times concentration of A. This is the integrated rate law here. And this is one way of expressing it. There are some other ways of expressing it, which I can actually show you right now. Let me do that right now. Another way of expressing this law right here, and what I'm going to do is show it up here, is concentration of A is equal to the concentration of A initial times E to the minus KT, all right? Now, this equation is more useful if you're trying to find A, the concentration of A at a particular time T, all right? I would use this equation if I'm asked to find T, all right? or K, depending on what you're given in the question. All right. So it all depends on, the question that you're dealing with. Another thing I want to point out too is that graphically speaking, this equation is more useful because basically this equation would be in the form of y is equal to C minus mx, right? Now t would be on the x-axis and y, the ln a would be on the y-axis. So therefore the intercept c would be on the, would be equal to ln a initial. So let me see if I have the graph for it here. Let me scroll back up here in my PowerPoint. Okay, so this is an example that was covered in the video. Basically, this is the plot of ln A. In this case, this is the reaction here. And this would be A, which would be dinitrogen pentoxide. It's a first order reaction. So this is the natural log of the concentration of nitrogen pentoxide. This is the time axis, and you see it's a straight line with a negative slope, and that negative slope would be equal to the K, the rate constant. Actually, well, minus K would be equal to this slope, which would be negative. All right. I'm sorry about this. Let me go back to the graph. Right. So that's basically for a first order reaction. All right. Okay. Let me go back to the table again, which summarizes the different types of equations. Okay, so go back to this again. Okay, so that's a first order reaction. And then for the second order reaction, then this would be the rate law. This would be the equation. Let me get rid of this. Okay, so this would be the integrated rate equation, right? 1 over the concentration of A is equal to 1 over the initial concentration of A plus KT, right? And in this particular case, the half-life is equal to 1 over K times the initial concentration of A, all right? So these two are the equations that you would use to determine, or, whatever calculation is involved, involving a second order reaction. These are the equations you would use. I just realized that there's something I skipped over. So let me go back to the first order rate equation. And that is the half-life here, right? This is the equation for the half-life for the first order equation. Half-life is equal to ln2 over K, all right? And one big difference between a first order reaction compared to the 0 and second order reaction is that there are no concentration terms involved in this equation for calculating the half-life. So what does this mean? This means that the half-life for a first order reaction is independent of the concentration initially of your reactant. So the first order reaction is kind of unique in that sense, because you'll notice that in the case of the 0 order reaction and the second order reaction, there's a concentration term in both cases. That is not the case for a first order reaction, all right? One more thing I want to say here, and that is in the case of a second order reaction, the plot on a graph that can be used would be plotting 1 over A versus T, because in this particular case, let me go back to my pen function here. In this particular case, the 1 over A would be on the y-axis, the T would be on the x-axis, the slope would be a positive slope, which would be the K, and the intercept would be the 1 over A initial, all right? So if you plot T versus 1 over A, or I should say the other way around, 1 over A versus T, then you're going to get a straight line, positive slope line, where the slope is equal to the rate constant, all right? Okay, so I just thought I should briefly go over that before we look at the questions involving these types of reactions. Okay, so firstly, any questions about what I just covered? Any questions? Any questions? Any questions? Okay, so let's move on to, I think it is question number 5 in the assignment. So the question says the rate constant for the first order decomposition of, and it gives you the reaction, is 6.32 times 10 to the minus 4 seconds to the minus 1. All right. So the question is asking in the A part, what is the concentration of N2O5 remaining after 2 hours if the initial concentration of N2O5 is 0.500 M? Okay, so the first thing that would come to mind when solving this problem is the equation for the first order reaction. And that equation, just to remind you, let me go to my writing function here. So let me squeeze that equation up here. That equation, hold on 1 minute. Okay, that equation will be Ln concentration of, well, in this case, it's dinitrogen pentoxide, so I'm going to use that formula, is equal to Ln, the initial concentration of N2O5 minus KT, all right? So that's the first thing that would come to my mind when trying to solve this problem, because after all, the question says it's a first order reaction. All right, so let me go back to my writing function here. Oh, no. Okay, I realize I did something wrong here. Let me go back to this. Okay, so let's look at what the question has given us in the A part. The question says that the initial concentration of N2O5 is 0.500 M, right? The question also gave us the rate constant, which is 6.32 times 10 to the minus 4 seconds to the minus 1. And the question gives us the time, 2 hours, all right? And the question is asking, what is the concentration of N2O5 remaining, all right? So basically what the question is asking for, and I just realized I made an error here. There should be no 0 here, right? That is the concentration of N2O5 at time t, all right? So what the question is actually asking for is this right here, right? The concentration of N2O5. Okay, another thing I should say here, now that I've noticed this here, is that the other form of this equation would be concentration of N2O5 is equal to the concentration of N2O5 initial times e to the minus KT, all right? Now, this would be the form that would be most useful because you can calculate the concentration of N2O5 directly. Okay, so now that I've explained all of that to you, how would you solve this problem? Anybody?
Could you start plugging in the values? So 0.500 M for the initial value.
So the concentration of N2O5 would be equal to 0.500 M. Okay, what else?
And then minus 6.32 times 10 to the negative 4.
Well, don't forget this. Remember this? The E?
Oh, okay.
Exactly. So you need to include that as well. And then the minus KT. Now, one thing I need to point out here, and this is kind of like a trick part of the question. They gave the time in hours, but here the units of K is seconds to the minus 1. So what do you think we need to do as far as that part is concerned?
You have to convert it to 7200 seconds.
Okay, so the 6.32 times 10 to the minus 4 seconds to the minus 1 multiplied by the 2 hours. And as you correctly said, you need to convert that to seconds, right? So the relationship between the seconds and the hours unit would be 3600 seconds for 1 hour. So we're going to put 3600 seconds down here. Actually, 72, you're right, 72. Well, actually, no. 36. The 72 comes when you multiply. So let me erase this here. So 3,600 seconds will go up top and 1 hour below, so that the hour units will cancel out. This seconds will cancel out with the seconds to the -1. And then we just do our number crunching on our calculator, which I've already done. So according to my calculation, the answer I got, and folks, please, please, please check to make sure I'm doing the right thing, because I'm not infallible. I can make mistakes when I do these things, but I'm quite sure I'm right about this one. But check behind what I do so that you're ensuring that I'm doing the right thing. Okay, so that's the answer for the A part. All right. Okay, any questions about this one? Any questions? Any questions?
Did you get the E because you canceled out the ln on the other side?
Yes. In fact, and again, this goes back to what you should have learned in algebra. Let me just show you how that is done. Since you asked that question, let me get out of this here. And let me, okay, come on. Let me clear this. Okay, so if you remember, one form of the equation, ln A, is equal to ln A0, whoops, minus KT. What am I doing? Minus KT, let me erase this here. Right, so this, as I said before, is one form of that equation. Now, you should know or remember from your algebra that if you were to subtract ln A0 from both sides, then you're going to get ln concentration of A minus, what's going on with this thing here? Minus ln concentration of A0 is equal to minus KT. And then you should know from your algebra that this part here would be equal to ln concentration of A over the concentration of A0, right? And that would be equal to minus KT. And then what that means, therefore, is that the concentration of A over A0 will be equal to E to the minus KT. All right, which means that concentration of A is equal to, oh, this should be A0 here, by the way. So that becomes concentration of A is equal to concentration of A0, E to the minus KT. So basically, this is one form of that expression or relationship. And this here, which I had originally, would be another form. So I hope that answers your question. Who asked that question, by the way? I don't know.
It was me, Rena. I think I solved it in a different way, but we got the same thing.
Oh, okay. All right. Yeah. There's more than one way of doing that transformation. Okay. Any other questions before we move on to the B part? Any other questions?
If you were to do the first equation with the natural logs, would you get the same answer?
Exactly. It's just that, yeah, what you could do is plug the numbers in for initial concentration of A, time, and K, right? And that will give you ln A, right? Right, so ln A would be equal to whatever you got as a result of that. And therefore, concentration of A will be equal to E to whatever that is. And you should get the same result. The only reason why I choose to use this method is because this method allows us to calculate A directly. All you have to do is plug in the numbers for these values here in this equation, and that's it. You get your A value. All right. Okay, any other questions? Any other questions? All right, so let's move on. Okay, why is this thing? My laptop is acting up. I can't seem to, hold on. Okay, I don't know what's going on here, folks, but my laptop seems to have. Oh Lord, I don't know what's going on here. Okay, now we're in business. Let me okay. All right, so that was the A part. So the B part, let me scroll down here, is asking how long will it take for the time required for 90% of the N2O5 to decompose, all right? So the rate constant is still going to be the same, right, from earlier. The initial concentration is going to be the same, but as you're going to see, that's not really important, but you can still use that value. But the rate constant is going to be the same, all right? Now, here's the thing. The question says that 90% of the N2O5 will decompose. Okay, so let me hear from you guys how you tackle this particular part. Any ideas? Okay, let me ask you this. So the question is asking for the time, right? Because the question is asking, how long will it take for 90% of the N2O5 to decompose, all right? So you could use either one of the two forms of the equation for the first order reaction, right? So you could use, let me go this here. You could use, okay, why is this? Let me write it up here. You could use Ln concentration of A is equal to Ln concentration of A initial minus KT. You could use that form, or you could use, what's the other one? Oh no, I wouldn't use, well, you could use it, but it would take a longer process. You could use the other form. Concentration of A initial is equal to E to the minus KT. Now, I'm sorry, I'm rushing. Let me do this again. You could use, what was I saying now? Concentration of A is equal to concentration of A0 times E to the minus KT, all right? Now, of these two, I would prefer to use this one here, right? Because you can use that to calculate T directly. All you have to do is rearrange it algebraically, all right? So, now that I've said all that, how would you tackle this problem?
Would you put T times the natural log of A equals the natural log of A initial minus K?
No, I don't think that's the correct algebraic result. You want to isolate T, right? So that means you want to carry ln A initial over here, right? How would you get rid of this on the right side?
Subtract it.
Exactly. So when you subtract it, you're going to get ln concentration of A minus ln concentration of A initial, and that would be equal to minus KT. And you can actually simplify this a bit again, if you remember what you learned in your algebra classes. This here would be equal to ln concentration of A over concentration of A initial, right? So we can kind of make it more simple, and that would be equal to minus KT, right? So how would you get T by itself?
Add K to the left side.
You sure about that? Anybody else want to help her out?
Would you divide by K?
Okay. Actually, you divide by more than just K. I would divide both sides by minus K. Right? Because you want to get T by itself, right? So T would be equal to ln concentration of A divided by concentration of A initial divided by K. And then all we have to do is plug the numbers in. So here's the thing. We know what the initial concentration of A is, 0.500 M. Now the question now becomes, what's the concentration of A at that time? Because remember the question says that 90% of the N2O5 has decomposed. So how would you determine the concentration of A at that time?
Would it be 100 minus 90? So it's 10%.
Exactly. So basically it's 100% minus 90% multiplied by 0.5. All right. And that would be equal to, what was it? Let me do that. So that would be 0.0500. All right. So basically, you plug everything now into this equation. ln, concentration of A, which is 0.0500 M, divided by 0.500 M. All of that divided by K. What was K? K was 6.32 times 10 to the minus 4, seconds to the minus 1. And according to my calculations, that works out to be equal to 3.64 times 10 to the 3 seconds. And that would be the final answer. All right. Okay, any questions about this one? Any questions?
Would you not have a negative K?
Right. The answer is still the same, but yes, you're right. Negative sign should be here somewhere. But the result is still going to be the same. I did not include the negative sign there. Okay, thank you. Whoever said that. Who said that?
McCoy.
McCoy. Thank you, Miss McCoy. All right. Any other questions about this one? Any other questions? Any other questions? Okay, is it okay for me to clear this? Is it okay for me to clear this? Going once, going twice. All right, I'm going to clear it. So let me clear all drawings. Okay, so if you understood what I just did in B, then you should be able to understand how to solve the C part. So let's hear your suggestions. Now, in this case, it says, how long will the reaction take for 90% to remain? Let's scroll down a bit here. So let's hear your suggestions.
You do everything exactly the same, but instead of doing 100 minus 90%, you just take 90% of the 0.500
Exactly.
M.
So first thing I would do is calculate the concentration of A, which would be equal to 0.9 times 0.500 M And that would be equal to what? 0.9 times 5. I'm sorry, 0.9 times 0.5. So that'll be 0.450 M. And T would be equal to minus natural log of 0.450 M divided by 0.500 M divided by K, which is 6.3, 2 times 10 to the minus 4, seconds to the minus 1. And again, according to my calculations, I got 167 seconds. All right. Now, one thing I want to say here, and that's in relation to both the B and C part. You did not need to use this here, the initial concentration, because what you could have done is that in the case of the C part, you could just simply say that the concentration of A is equal to 0.9, the concentration of A initial, which means that the concentration of, which means that, the concentration of A over the concentration of A initial is equal to 0.9, right? And therefore, this value here could go where this is in that parentheses right here. All right, you could simply replace all of this here with 0.9 and you're going to get the same result. All right, so the point I'm getting at is that you did not need to know what the initial concentration was. What you do know is that the ratio of the concentration at time t to the initial concentration is 0.9, because the question says 90% of the initial concentration remains at this time. All right, so that's just an additional point I want to make. And in the case of the previous question, this ratio here in the previous question would be equal to 0.10, right? And you plug it into this equation and you get the same answer as we got before. All right. Okay, any questions about that? Any questions about the C part?
Did you put the negative on top next to the natural log to replace the negative on the bottom?
Yeah, exactly. It doesn't matter where, actually. You could have placed it here
Okay.
or place it down here. Same result, yes.
Okay, just making sure. Thank you.
No problem. Okay, any other questions before we move on to the D part? Any questions? Going once, going twice? All right, so the D part says, how long will it take for 50% to remain? Okay, so what comes immediately to mind when you see that question? How long will it take for 50% to remain? So presumably they're talking about 50% of the reactant.
Do you do the same thing except just like where you would do like the 90% before, it'd just be 50%?
Okay, so you're saying T in this case will be equal to minus ln 0.5 divided by K, right?
Yes.
Okay, now remember we talked about the half-life. By definition, the half-life is the time taken for half the amount of reactant to react, right? So this is basically asking for the half-life. It doesn't say so directly, but that's what this question is saying, right? So you're right, you could use this way of approaching it, but you can also use the half-life formula, which is basically the same thing, ln2 over K, right? So, you know, because it turns out that minus ln 0.5 is the same thing as ln2, right? So I'm just going to use this equation here, ln2 divided by K, which is 6.32 times 10 to the minus 4, seconds to the minus 1. And according to my calculations, this works out to be equal to 1.10 times 10 to the 3 seconds, all right? And that's basically how that is done. Okay, any questions about that particular problem?
Just to be clear, when you get down to the ln2 divided by the 6.32 times 10 to the negative 4, when you get that answer, do you want to divide that in half because of the t half?
No, that equation directly calculates a half-life. So you don't, after you put the numbers in, you don't need to do anything else.
Okay.
You see what I'm saying?
Yeah.
Yeah, so after you get that answer, don't divide by anything. That would be the half-life. All right. Okay, one more thing I want to talk about before we take our first break. Let me get out of this here. And let me go back to my writing application here. And let me clear this up. Oh, so much mess here. Is it okay for me to get rid of this here? Going once, going twice. All right, I'm going to get rid of it. So let me do this. Let me clear all drawings. Okay, specifically as it relates to the first order reaction, another thing that you should understand is that for first order reaction, the half-life is constant. For a first order reaction. And that becomes clear again because of the equation. The equation for the half-life of a first order reaction is ln2 over k, right? This is a constant and this is a constant, which means that half-life is a constant for a first order reaction. And that's kind of important, not only for this chapter, but later on, when we start looking at nuclear chemistry, you're going to see that nuclear reactions are pretty much, or nuclear decay, I should say, are pretty much first order reactions, all of them, right? And therefore, sometimes it is very easy to determine how much of a substance remains after a certain number of half-lives passing by. So let's say you have a reactant A and the concentration of A is that value, whatever that value is. After one half-life, if it's a first order reaction, then the concentration of A is reduced to half the initial concentration of A. So this is the initial concentration of A. This is half the initial concentration of A after one half-life, and then after another half-life, the concentration is reduced by another half to get 1/4 of the original concentration of A. And you can imagine what's going to happen after the third half-life. What's going to happen? The concentration of A would be what? Anybody? It should be easy for you to figure it out. What will be the concentration of A after the third half-life? What is half of a quarter?
1/8.
Exactly. And then the next half-life, what would be the concentration?
1/16.
Exactly, and so on and so forth, right? So basically, if N, and I think I have a table in the PowerPoint, but I won't go to it. Basically, if N is equal to the number of half-lives, then the concentration of A would be equal to, hold on, let me see here, would be equal to the initial concentration of A divided by 2 to the N, all right? So that's a relationship between the current concentration of A and the number of half-lives that has passed by, right? So that kind of makes things easier for us to calculate if you know the half-life and know how much time has passed, and if you see that the number of half-lives is equal to a multiple number, or an integer, I should say, then you can just simply use this formula here to calculate the current concentration of A. Okay, I'm going to stop here. I'm way past my 50-minute time before our first break. So we're going to get back here at 11 o'clock. All right. So you can go and take your bathroom break or whatever. Okay, I am back. So before I move on to the next question, I just want to say, and some of you may have seen this in the announcements I made. I think I posted it this morning. So most of you turned in assignment number 1 on time, but there are 4 of you, I think, who have not turned in assignment number 1 yet. So if you have not done so yet, please do so by midnight tonight. After that, I will not be accepting any more assignment number 1. So if you have not done so yet, you have until midnight tonight to do so. All right. That's very important because what I plan to do next is post the answer keys, or the answer key, I should say, to assignment number 1 for you guys to look at. And also, as I said earlier, I'm planning on sending you guys, for those of you who have turned in already your assignment number 1, I plan to email to you guys your graded work so that you can compare your answer to the answer keys. And if you have any questions, of course, please feel free to contact me concerning that. All right. Okay. So with that out of the way, we're going to scroll down to question number 6. Now, in the case of question number 6, it says, excuse me, the differential rate law for the association of iodine atoms to molecule iodine is, and it gives you the equation here, and it says, is given rate is equal to K times the concentration of I squared. So this is the rate law right here, all right? And it says where K is equal to 7.0 times 10 to the 9, all right? So
We can't see your screen.
Oh, I'm sorry, thank you. I keep forgetting to do that. Okay, sorry about that. So, hold on 1 minute. Yes, okay. So this is the question right here. It gives you the equation for reaction, and it gives you the rate law, and it says that K is equal to 7.0 times 10 to the 9, all right? So the first question, the A part, is asking, what are the proper units for K? So who would like to take a stab at this one? Well, before you even do that, let me remind you of the equation for this reaction, for this type of reaction. The first thing I notice here is that the reaction is second order with respect to the reactant, right? So that means that the equations we'll be using would be this equation here and this equation, right? This is the equation which relates the concentration to time, and this equation here is what you use to calculate the half-life. So what I'm going to do is go back to this, and I'm going to write down, oh shoot, sorry. I am going to write down the 2 equations that will be useful. I'm going to squeeze it over here. So one equation would be 1 over the concentration of A is equal to 1 over the initial concentration of A minus KT, or plus KT. Make sure. Give me 1 minute here. So this would be plus KT, and the half-life equation is equal to 1 over K times concentration of A0, all right? So the question is asking for the units of K. And in order to answer that question, I would use this equation right here, right? And the reason why I would use this equation here is because here is the time term, and here is the concentration term. So if we know the units of time, and if we know the units of concentration, then we can determine the K units by simply rearranging this equation to give 1 over the half-life times the concentration of A initial. So based on this arrangement, what would you think the units of K would be? Anybody?
Would it be 1 over molarity times seconds?
Okay, so you're saying 1 over ms? That
Correct.
would be indeed correct, or you can represent it as m to the minus 1 seconds to the minus 1. All right, both are just as valid in terms of the answer to that question. Okay, very good. So let me see here. Okay, so that's the answer to the A part. Now the B part says, if the initial concentration of iodine is 0.40 m, calculate the concentration of iodine when the time is 2.5 times 10 to the minus 7 seconds. Okay, so I would use this equation right here, right? Because they gave us the initial concentration, and they gave us the time, and they gave us the K, right? Which is this right here. Okay, so I need somebody to tell me what to write down based on that.
You would do 1 over 0.40 m, or you would write like 1 over I, the concentration
Okay.
of I equals
Mm-hmm.
1 over 0.40 m,
Mm-hmm.
and then plus, in parentheses, 7.0 times 10 to the 9th. You could do like m to the negative 1, s to the negative 1, or
Well, that would be m to the minus 1,
mhm,
s to the minus 1, yeah, times.
times
In parentheses.
2.5 times 10 to the negative 7 seconds.
Okay, very good. So that would be the setup. And based on that setup, what I got when I did it myself, and again, please check to make sure I'm doing the right thing, but I got, as far as the other part of this setup is concerned, this part here works out to be equal to 1800 m to the minus 1, right? Or maybe I spoke too soon. Hold on, let me see here. This doesn't look right. Let me check this out. So this would be 2.5 times 10 to the minus 9 plus 2.5 times 10 to the minus 7. Okay, so hold on, wait a minute. Okay, I'm doing, okay, I thought I did the correct thing, but I think this is not quite correct.
When you were typing it in, you said 2.5 times 10 to the minus 9. It would be 7.0 times 10 to the minus 9.
Oh, okay. So the minus 7 is correct. It's a minus 9 that's not correct. That should be 9. All right, so maybe that's where I made my error. Thank you for pointing that out. So let me do this again. 7 times 10 to the 9 times 2.5 times 10 to the minus 7. So yes, I actually got 1800 here, m to the minus 1. And then when I add that to 1 over 0.4, so let me see what this gives, 0.4. Okay, so this still works out to be 1800 m to the minus 1. All right, because I have to round off to the highest number, the highest place sig figs right here. So this becomes 1800 m to the minus 1. So remember now, let me do this here and scroll down a bit. remember now, what the question is asking for is the concentration of I. Now, this here is a concentration of, well, 1 over the concentration of I, not I0. So that means that in order to calculate the concentration of I, let me do this over here. The concentration of I would be equal to 1 over 1800 m to the minus 1. And when I did that, 1 divided by 1/800, the answer I got is 5.6 times 10 to the minus 4 m. And that's how the B part is done. All right. Okay, any questions about this? Any questions? Any questions? Okay. Is it okay for me to clear this?
I have a question.
Yes, ma'am.
When you're doing the math, like when you do the 1 over 1800 m to the -1, do you include the -1 in your calculation?
You mean the m to the minus 1?
Mhm.
Well, that won't be part of the calculation. It's kind of like part of the setup.
It's like a
Um,
given for the unit.
Exactly. Exactly.
Okay.
But of course, you recognize where we get this from. We get that
Right.
from because just for the benefit of the rest of the class, those two will cancel out. So you're left with m to the minus 1 here.
Okay, I just want to
Alright.
make sure you didn't calculate it into the answer.
Right, exactly. You see, what you have to remember, units are basically labels, right? Which is associated with the type of quantity that, that it's attached to, basically. Okay, any other questions about this one? Any other questions? Okay, so I take it it's okay for me to clear this, right? Going once, going twice. All right. So the next question has to do with the half-life. So how would you tackle this one?
I don't have the half-life equation in front of me with that graph, but you would use the half-life equation to answer it.
Let me remind you of what that equation is. Oops, I'm sorry. Why did I do that? Okay, so let me remind you of what the half-life equation is for a second order reaction. Its half-life is equal to 1 over K times the initial concentration, in this case, of I0, all right? So that will be 1 over K, and K, if you remember, is 7.0 times 10 to the 9, m to the minus 1, s to the minus 1, times the initial concentration of I, which is the 0.40 m, and that's it. Put those numbers in the calculator, do your number crunching, and you're going to get 3.6 times 10 to the minus 10 seconds. And that's how you do that. All right? So that one is relatively simple. Any questions about that one? Any questions? Any questions? Okay, so let me clear all this and move on to, I think, the last question, or the last part of that question, which says, if the initial concentration of I is 0.80, how much time will it take for 75% of the iodine atoms to react? Okay, so what would be the very first thing you would do in this particular case? Anybody? They gave you the initial concentration, and the question says that 75% of the iodine has reacted, and it's asking for how much time. Let me help you out. The equation I would use would be this equation right here. That's the integrated rate equation for the second order reaction. All right, that's the equation you would use. All right. So how would you tackle this problem?
You need to isolate T.
Okay, so how would you do that? So far, I've been hearing only one voice contributing to the class, so I need the rest of you to participate. And maybe I should start calling names. Okay, so how would you isolate T? Anybody? Preferably somebody who has not contributed before. How would you isolate T on one side of the equation?
We just did this one. I mean, one of this too.
We did something kind of similar, but not the same. I think we did it for the zero order reaction or first order reaction.
You gotta divide.
Well, division will come later, but you have to do something else. You have to do something before you do that.
Subtract the first part and then divide by K.
I would subtract this from both sides, right? If I do that, I'm going to end up with 1 over concentration of I minus 1 over the initial concentration of I, and that would be equal to KT, right? And then what? This is where the division comes in. So what do you divide both sides by?
K.
Exactly. So when you divide both sides by K, let me do it up here, you're going to get 1 over K times 1 over the concentration of I minus 1 over the initial concentration of I, and that would be equal to T. So this is the equation you're going to use. All you have to do is plug the numbers in. So this would equal to 1 over K, which we had as 7.0 times 10 to the 9, m to the minus 1 seconds to the minus 1, times 1 over the concentration of I. Now here's where the 75% comes in, right? It says that 75% of the iodine reacted, which means that 25% would have remained. So that means that the concentration of I would be equal to 0.25, multiplied by the initial concentration of I, which is 0.80 m. So that's a quarter of 0.8, which would be 0.10.
Is that a 2, Professor?
I'm sorry?
0.25?
Yeah, 0.25. Because it says, notice how the question is worded, and this is very important. The question says that 0.75% of the iodine atoms reacted, right? So what that means is that
25%.
right, 25% would be the amount remaining. So that's why we use 0.25 here, right? So it's 0.25 times 0.8, and that will give you 0.2. I'm sorry, I misspoke. The quarter of 0.8 would be 0.20 m, right? So that concentration of iodine would go here, 0.20 m minus 1 over the initial concentration of iodine, which is 0.80 m. And when I did that calculation, I got 5.4 times 10 to the minus 10 seconds. And that would be the final answer for that part. All right. Okay, any questions about this particular problem? Any questions? Any questions? All right. Take it, it's okay for me to clear this, right? Going once, going twice. All right, so let me clear this. And let me do that, and let me scroll down. And now we're going to move on to question number 7. Okay, now question number 7 deals with this whole concept of activation energy. Again, this is something you should have read upon in the videos that I've posted in Canvas. Just to give a brief overview, basically what deals with is a situation where we try to understand what is actually happening at the microscopic level when you have molecules reacting to form products, right? And people have looked at this extensively, and they have come to the conclusion, I think Arrhenius is one of those guys who studied this. They have come to the conclusion that whenever you have molecules that could potentially react, not all, well, basically what is thought is that the molecules that are reacting will collide first, right? And then after the collision, you have bond breaking and bond making, which results in the formation of products, right? Now, what eventually was discovered was that not all the collisions would have successfully result in product formation. And it turns out that the extent to which products are formed is dependent on how energetic the molecules are when they collide. In other words, in order for the molecules to collide and form products, the colliding molecules must have a minimum amount of energy. That minimum amount of energy is known as the activation energy, all right? So basically the way the collision theory works, and that's a theory that is used to explain what I just talked about. The way the collision theory works is that if the molecules collide and they don't have at least the activation energy, they'll simply collide and bounce off each other without any changes. Now, if the molecules have at least the activation energy, then they will collide, bond breaking will occur, bond formation will take place subsequently, and therefore products will be formed, all right? So the activation energy is considered to be the energy barrier that the molecules that are reacting must achieve in order for a reaction to take place or products to form. And there's an equation which relates the activation energy to the rate constant, and this is based on the collision theory. And that equation, let me just go to this here, or actually go to this here, and write down that equation. That equation is K is equal to A times e to the minus EA over RT, all right? And let me just briefly explain what each of these terms are. So K is the rate constant. A is what is called the frequency factor. EA is the aforementioned activation energy. R is the molar gas constant. And let me just say something about the molar gas constant for a minute before I move on to the other terms. The molar gas constant that you're probably more familiar with is 0.0821 liters atmospheres over mole Kelvin, right? But there's another value or another way of expressing the molar gas constant based on different units. And that is 8.31 joules per mole Kelvin, all right? Now, this is the one that you're going to use in where R is in this equation right here, all right? So you're not going to be using this one. This one, we tend to use this one when it comes to the gas laws for the most part, all right? But this one here we use in the case of this equation here, which is called the Arrhenius equation. Arrhenius, I hope I'm spelling this right. Equation. This is the Arrhenius equation, all right? So that's the R value that you're going to use in the Arrhenius equation. And then now, the last term here is the temperature of the reaction, which must be expressed in Kelvin. All right? So that's the equation which relates the rate constant to the activation energy and also the rate constant to the temperature, all right? Now, if you look at this equation and inspect it more carefully, you'll see that there are some interesting relationships that you can determine based on comparing rate constant to different terms and holding other terms constant. So for example, let me squeeze it over here. Let me just draw a line here to avoid confusion. If you look at this equation here, you'll notice that as temperature increases, right, K would increase, which makes sense, right? As the temperature increases, of course, what will happen is that more molecules will have at least the activation energy value, which means that more products will be formed at a faster rate, all right? So as temperature increases, the rate constant increases. If the rate constant increases, then the rate increases, all right, as the temperature increases. Okay, so that's one thing I want to point out. Another thing I want to point out is that as the activation energy increases, the temperature, the K value will decrease, all right? And that also makes sense because if the activation energy is high, if the energy barrier for the reaction is high, that means that there will be fewer molecules that would be able to be converted to products, which means that the rate would be less and therefore the rate constant would be lower, all right? And this aspect here is important when it comes to catalysis, right? Because as you should have read in, or you should have seen in the videos that I've posted, we talked about the fact that catalysts are substances which, when added to the reaction, it provides a different mechanistic pathway of lower activation energy. So if the activation energy is lowered, that means that there is a corresponding increase in the rate constant, all right? And there are several examples, especially when it comes to biological systems, where we can apply this idea. For example, if you were to take, and this is something you can do at home actually, if you were to take ground beef, right? So you buy the beef, beef liver, I should say, at home. If you take it home and then you cut it up or grind it up into smaller pieces, and then you add hydrogen peroxide to it, what you'll see is a rapid formation of bubbles. Now, the reason why that happens is because when hydrogen peroxide decomposes, it forms it forms water and oxygen gas, right? So the bubbles that you see here is due to the oxygen gas. Now, this reaction is sped up by an enzyme which is found in ground beef known as catalase. All right? So what catalase does is that it provides a different mechanistic pathway of lower activation energy. And because the activation energy is lower, more of these molecules will have at least the activation energy, which allows it to be converted to oxygen, and therefore you have the more rapid formation of oxygen gas. Without the catalase, the reaction will take place, but at a much slower rate, all right? So that's just one example. And there are several examples of catalysis that was discussed in the videos. So if you need to refresh your memory, you probably want to go back and watch those videos which discussed different types of catalysis in detail, all right? Okay, so I just thought I should mention that so that we can go ahead and look at the question here. So, one more thing I need to say. Let me go back to this right here. So this is one form of the Arrhenius equation, right? But you can also express this in another form. In fact, let me get rid of all this here and let me write down this form of the Arrhenius equation, which is K is equal to A e to the minus EA over RT. And then there's another form of this equation, which is ln K is equal to ln A minus EA over R times 1 over T, all right? So these are two different ways of saying the same equation or relating the rate constant to temperature and activation energy and so on, all right? There's yet a third way of expressing this relationship, and that is basically, well, before I move on to that, there's something I need to mention about this particular way of expressing it. This equation is very useful because if you carry out experiments where you can get different values of K for different values of T, then what happens is that if you plot ln K versus 1 over T, you're going to get a straight line graph. This will be plotted on the y-axis. The 1 over T will be plotted on the x-axis. And what you're going to get is a line with a negative slope, which would be equal to minus EA over R. And ln A would be the y-intercept, all right? So basically, you're going to get a graph which looks like this. If you plot ln K versus 1 over T on the x-axis, you're going to get a graph looking like this with a negative slope, where the slope would be equal to minus EA over R, and the intercept would be equal to ln A. All right? So this is basically useful if you're doing an experiment where you're getting different data values for K and T, right? And you can use it to determine the activation energy of the reaction. Okay, one more thing I want to say about this relationship. There's another way of expressing it, and that is a situation where, let's say that you did an experiment where the value for K is K1 and the corresponding temperature is T1, and the value for K is K2 for another temperature value T2. In that case, the relationship will be ln K1 over K2 will be equal to minus EA over R times 1 over T1 minus 1 over T2. So this is yet a third way. So I'm just going to put an asterisk beside the different ways of expressing the relationship between rate constant and temperature. This is one way. In fact, let me number them. This is one, the first one I mentioned. This one here is number 2. And then this one here is number 3. All right, so these are 3 different ways of relating the rate constants to temperature. All right. Okay, so I just thought I should discuss that before we move on to the next question. All right, so before we move on to the question, any questions about what I just covered? Any questions? Any questions? Any questions? Going once? Going twice? Okay, so let me get out of this here. And let me start by looking at this question here, which says, calculate the activation energy for the decomposition reaction of NO2. And it gives you the equation. And it gives you that at 300, let me get my writing thing going here. So it says that at 300 degrees Celsius, the rate constant is 5.7 times 10 to the minus 1. But at 230 degrees Celsius, the rate constant is 2.7 times 10 to the minus 2. All right. So the question is asking for you to calculate the activation energy. So the form of the equation I would use is the one I just talked about. And that is ln K1 over K2 is equal to minus EA over R times 1 over T1 minus 1 over T2, all right? So that would be the form of the equation that I would be using. So basically what it comes down to is identifying the different terms according to the question, all right? So here's where you're going to come in. You're going to tell me what is what in order to answer this question right here. Well, firstly, before we do that, how would we rearrange this equation to solve for the activation energy, which is this right here, EA, all right? So what would you do? Some algebra will be involved, of course. So anybody, what would you do?
You would divide the 1 over T1 minus 1 over T2 on both sides.
Okay, so if you do that, you're going to end up with minus EA over R would be equal to ln K1 over K2 divided by 1 over T1 minus 1 over T2. You're correct. Okay. And then what?
Plug in the values.
Well,
Well,
what
first you need to change the Celsius to Kelvin.
well, that too, but what I would do also is make sure the R gets over here. So how would you get rid of the R on the left side?
Oh, I'm sorry. You would multiply R on both sides.
Right. And not only that, but I'll also multiply by negative R on both sides because you want to get rid of the negative side.
Gotcha.
Right? So multiply negative R on both sides, you're going to get minus R ln K1 over K2 divided by 1 over T1 minus 1 over T2. And you're correct about the conversion to Kelvin values, right? So the 300 here, if you add 273, you're going to get 573 Kelvin. If you add 273 to this, you're going to get 503 Kelvin. So I'm just going to put those here, right underneath those values, right? So now all we have to do now, and this will be equal to EA, of course. So all you have to do now is plug in the values for the activation energy. Now remember, the R must be expressed as 8.31 joules per mole Kelvin multiplied by ln K1. So what is K1? K1 would be the initial activation energy here, right? So this is K1, and this would be K2, right? So K1 would be 5.7 times 10 to the minus 1, m to the minus 1, s to the minus 1, divided by 2.7 times 10 to the minus 2, m to the minus 1, s to the minus 1, right? And we put that in parentheses, and then we divide all of that by 1 over T1. T1 would be equal to the 573 that we calculated earlier, Kelvin, minus 1 over T2, which would be 2.7 times 10 to the minus, no, I'm sorry, big mistake. T2 would be 503 Kelvin. 503 Kelvin, all right? Okay, and then we work this out. And according to my calculations, when I did that, I got 1.04 times 10 to the 5 joules per mole. And just to explain how we get the units, the Kelvin units will cancel out here and here. The m to the minus 1 units will cancel out here and there. So the only unit remaining would be joules per mole unit, which is what we end up with in the final answer. And that's basically how that is done. Okay, any questions about this particular problem? Any questions? Any questions? No questions? Okay, so is it okay for me to clear all this? Going once, going twice? Okay. I'm going to clear it now. And let me do this. And let me scroll down to question number 8. Now, question number 8 deals with something I kind of alluded to in passing a while ago. It deals with this whole concept of the mechanism of a reaction. So again, this is covered in the videos that I've assigned to you guys to watch. But just to briefly describe what we're talking about here, when we're talking about a mechanism for a reaction, we're talking about a detailed step-by-step description as the reactants is converted to products, right? And this whole concept of mechanism is very important, not only in the field of chemistry itself, but all other related fields. For example, I don't know how many of you are planning to pursue medicine or pharmacy as a career, but what you'll find is that one very important aspect of those fields is understanding the mechanism of drug action. And basically, what is involved is basically what I just said. You have to understand what happens at each step of the process. And there's a whole area in medicine and more specific in pharmacy known as pharmacokinetics, where basically that's the concern. That's the area of study which deals with how fast drugs are, how should I put this, metabolized in biological systems, and the detailed step-by-step mechanism that is occurring as the drug is going through the changes. All right. So what we're learning here is basically the basis when it comes to chemical kinetics and mechanism is the basis for all of that you'll be studying later on. If, as I said before, you plan to do medicine or pharmacy. All right. And maybe even other fields like veterinary medicine and so on. Okay, so some terms that I need to remind you of. Let me go back to this right here. And let me get rid of this here. So we talked about the mechanism. So basically the mechanism is the sum total of the different steps, right? So I'm just going to make up a hypothetical example here. So let's say you have A plus B going towards C, all right? And then we have to account for the mechanism of this reaction here. And let's say that one possible mechanism would be A forming an intermediate D, and then D forming an intermediate B, or D reacting with B. So let me take this out and put D reacting with B to form the final product C, right? So this is the overall reaction. And this down here would be the mechanism, right? And as you can see, this is a simple two-step mechanism. So this is step one, this is step two, all right? So basically in any mechanism, first thing I'm going to say is that in the mechanism as it relates to the overall equation, whenever you add all the equations in the mechanism, you should get the net overall reaction. So you'll notice that when you add these two, you're going to have D on this side, D on this side. And what you should have learned in General Chemistry 1, and if I'm not mistaken, this would be when you learned about net ionic equations, you should have learned that whenever you have any common items on both sides, they'll cancel out. So in this particular case, the D's will cancel out, right? So what will you be left with? A plus B to give C, which is the same as the overall reaction, right? And this is true for every mechanism. When you add up all the steps in the mechanism, the result should be the overall net equation, all right? Another thing I want to mention here is that there's one substance which is used up here and another substance which is, one substance which is produced here, which is D, and that same substance is used up in the second step, right? So we call D the intermediate, right? The intermediate is any participant in the mechanism that is produced in one step, but used up in a later step, all right? And then there's another term, which we met before, a catalyst. Actually, I don't think we met this before, or maybe I mentioned it. Now, a catalyst is basically a substance which is used up in a previous step and then reproduced in a subsequent step. So let me try another mechanism here. Let's say you have A reacting with, I'm going to say F, to form D, and then D, D reacts with B to form C and F. So in this case here, F is used up in a previous step and then regenerated in the second step. So in this case, F would be the catalyst. And typically what the catalyst does, as I think I mentioned before, is that it provides a different mechanistic pathway of lower activation energy, and therefore the reaction rate would be sped up, all right? Another term I need to introduce to you is this term of molecularity, all right? Which will become important in the question we're about to look at. So the molecularity is basically the number of particles that are reactants in an elementary step. So each of these would be elementary steps that is involved in the mechanism, right? So basically, to determine the molecularity of any step, all you have to do is look at the number of substances involved, molecules involved in each step. So in this case here, okay, let me erase some of this here so make things more clear. Let me erase this here. Okay, so going back to this first mechanism that we have over here. In this case here, for the first step, for step 1, the molecularity in this case is said to be equal to 1 because there's only one reactant involved in that first step. For step 2, the molecularity is equal to 2 because there's only 2 reactants involved in the first step, all right? Now, for most reactions, the molecularity of an individual step would be equal to 1 or 2, right? Because when it comes to situations where you might have 3 molecules coming together in an elementary step, the chances of that happening is virtually 0. It is very unlikely that you'll have, in a random situation where molecules are colliding with each other, it's very, very, very unlikely that you can have 3 molecules reacting at the same time to form a product in an elementary step, right? So typically we're not concerned with any situations where the molecularity is greater than 2, all right? Now, when it comes to the rate laws for these reactions here, for these elementary reactions, it's very easy to write them down based on the equation because, like for example, in the case for step 1, the rate of the reaction, the rate of that step would simply be equal to the rate constant for step 1 times the concentration of A, all right? So basically, in order for you to write down the rate law for that elementary step, you simply multiply its rate constant by the concentration of the reactant. So I'm just going to put K1 here for step 1, right? That would be the rate constant for step 1. And then I'll do the same thing for step 2. In that case, the rate would be equal to K2, right? So K2, I'm going to put here a constant for step 2, and that would be equal to the concentration of A times the concentration of B, all right? And that would basically how you write down the rate law for the elementary step. So you see that unlike overall reactions, when it comes to writing down a rate law of elementary steps, you can actually use the equation for the elementary step to determine the rate laws. You could not do that for the overall reaction, as we mentioned last time we were here, all right? Okay, one more thing I want to mention before we take our next break, and that is this whole concept of the rate determining step. The rate determining step of a multi-step mechanism. Rate determining step. In most textbooks, they abbreviate it RDS, all right? Basically, this would be, RDS. Basically, this would be the slowest step in the mechanism, all right? So if you have a multi-step mechanism, the slowest step in the mechanism is called the rate determining step. And if you think about it, it makes sense because if you think of a multi-step process, and this is true not only in chemistry, this is true in other areas where in order to reach a certain goal, there are several steps to get to that goal, So what you'll find is that in order to get to the final product of a multi-step mechanism, the rate of formation of that product cannot proceed faster than the rate of the slowest step, right? And what you'll find in chemistry, and this is true in particular when it comes to organic chemistry, pharmaceutical chemistry, and so on, what you'll find is that a lot of attention is paid to figuring out not only the mechanism of the reaction, but which step of the mechanism would be the slowest step, right? Because if you can figure out what the slowest step is, then you can alter conditions, especially if you understand what the structure of that particular intermediate at that point being formed. You can actually alter conditions so as to either favor the formation of the product or reduce the amount of product being formed, all right? So that's another important concept that you need to understand in order for you to basically appreciate the whole concept of, the mechanistic theory, all right? As I said before, there's a lot of applications of this when it comes to, areas in medicine, pharmacy, and so on. All right, I'm going to take a break right here, and then we're going to restart at 12 o'clock, all right? Okay, folks, I am back. So after discussing what I just discussed, I think we should now be able to do question number 8. And question number 8 says, oh, let me share my screen. I keep forgetting to do that. Okay, so here's question number 8. And it says, get rid of this thing here. Consider the following elementary reactions. And it gives you 2 equations, all right? And it says, what is the molecularity of each reaction, and write the rate law expression for each, all right? So we just discussed this before the break. So let me hear what you guys have to say about this. Let's deal with the first equation. What would you say is the molecularity of the first equation?
2.
2. You're absolutely 100% right. Hold on 1 minute. Let me do this. Okay, so for this one, the molecularity is 2. Molecularity. In fact, let me do this down here. For number 1, the molecularity is 2. Okay, and what would be the rate law for this equation? Rate is equal to what?
I put rate equals K1 times the concentration of carbon monoxide times the concentration of Cl2.
Correct. That is indeed correct. All right. So that would be the rate law for the first equation. Okay, what about the second one? What's the molecularity? Anybody?
I got 1.
That is indeed correct again. And what would be the rate law? Oh, and by the way, and I must apologize for it. It might be difficult for you to distinguish between these two, right? The first stroke here, that's an L, and the second one should be an I. But in any case, what's the rate law?
Rate equals K2 times the concentration of HCl.
Okay, very good. All right, so that's basically the answer for number 8, or the answers for number 8. All right, any questions about this? Any questions?
When you do the rate law, do you have to put K subscript 1 or K subscript 2? Because I see you didn't write that there.
Yeah, no, you don't have to, because it's not like in each case it's only 1 K you're dealing with. Now, usually, if it's if a multi-step mechanism is shown, as you're going to see further down, you have to make a distinction between the Ks within the same mechanism. So, like for the first step, you could call it K1, the second step K2. You know, it all depends. All right. Okay, so that's number 8. Any other questions before I move from this? Any other questions? All right, let me get rid of all this here. And then let me scroll down. Okay, now in this case here, it says, given the following mechanism of the reaction, and it gives you, you know, the different steps, 3 steps in this case. This question says, firstly, you need to identify intermediate and catalyst, if any, all right? So let me just remind you of what I said earlier before the break. Remember I said that the intermediate is a substance which is produced in one step and then used up in a subsequent step, right? While a catalyst is added or used up in one step and then reproduced in a subsequent step, all right? So that's the difference between an intermediate and a catalyst, all right? So Looking at the mechanism provided, can you identify an intermediate? And if so, what is that intermediate? So let me just write down here. I'm going to write down here, intermediate is equal to what?
I had a question about this part. Would we just
Mhm.
write CL and CLO, or do we have to write the 2CL and 2CLO?
You don't have to put the coefficient, just the formula for the substance.
Okay,
But you're right, it's CL and CLO. You're absolutely right, because the CL is used up here, or actually, I'm sorry, the CL is produced here and used up in the second step, and the CLO is produced here and used up in the third step. So these two would be intermediates. All right, and then, is it possible for you to identify a catalyst? And if so, what is it?
would the catalyst
CL.
be CL2?
Yes, indeed, right? So the catalyst would be Cl2 because it is used up in an earlier step and then reproduced in a subsequent step. Very good, okay. So that answers the A part. Now the B part is asking, what is the molecularity of step number 3?
Is it 1?
Okay, so let's remind ourselves of what we mean by the molecularity. Remember, the molecularity is the number of molecules involved as a reactant in a particular elementary step. That's a molecularity by definition. So would you want
So
to
it would be
rethink?
2.
Exactly, would be 2 because there are 2 molecules of CLO involved in step number 3. Okay, the C part says, which step determines the reaction rate, and write the rate law for that step. So of these 3 steps, which step would determine the rate of the reaction?
Would it be step 2?
Okay, so let's remind ourselves of what we mean by the rate determining step. What did I say about the rate determining step?
It's the slowest step.
Well, exactly, would be the slowest step. So which of the 3 steps you see here would be the slowest step?
The first one.
Exactly. So step number 1, whoops, what's going on with this thing? Step 1 is the slowest step. Oh, and we're not finished yet because we need to write down the rate law for that step. So what's the rate law? Rate is equal to? Anybody? Hello, anybody there? This should be easy.
One times CL, the concentration
sorry?
of CL2.
Repeat that.
Would it be K1
Mhm.
times the concentration of CL2?
Exactly, that would be it. All right. Okay.
I had a quick question about that.
Yes, ma'am.
I think you said that if there was an intermediate in that, you have to write it differently. Could you go over that? Because I didn't really understand.
Repeat what you just said.
Like for example, if CL2 was the intermediate, you said we can't have a rate law with that in it in one of your lectures. So I was wondering if you could go over.
Okay. Well, yeah, in fact, a subsequent question will deal with exactly what you are asking about. But just to give a brief answer to your question right now, basically, in order to write down the overall rate law, right, then the intermediate cannot be a part of that, because remember, the intermediate is used up and produced, or actually is used up, is produced in one step and used up in another step, right? And the chlorine here, the Cl2 here, actually is not an intermediate. It's a Cl that's an intermediate. But you know, give me a minute, and then I'll look at the next example or the next question. I think it's question 10. You're going to see where that what you just said is very relevant. All right. Okay. So let me. Is it okay for me to clear all this? Going once. Going twice. All right. Let me clear that. Let me do this. And let me move down to the D part. Okay, now in the D part, there's a typo. Let me just scratch out what we won't be answering in the D part. So for the D part, we won't be answering this part here. All right. So you can ignore that. But what the question is asking for us to do is write down the overall equation for the reaction. All right. And if you remember, I said, in order for us to get the overall equation, what we have to do is add up all the mechanisms and cancel out those items that will be common to both sides. So in actual fact, what I'm going to do is I'm going to scroll back up. Okay, so this is the mechanism. So my question to you at this juncture is, what will be canceled out on both sides when you add these all up?
I can tell right away the 2ClO is going to cancel.
Oh, the two ClOs, sorry, here and here.
Yes.
Yep.
And the 2Cls.
Very good. So therefore, what is left? Basically, what is left would be the answer. So it's going to be
Cl2
plus
2NO
right? And
reacts to give
then,
N2 plus
N2.
Cl2
nope. Oh yeah, you're right. Plus Cl2
plus O2.
plus O2. And that would be, no, wait a minute. The Cl2 would cancel out as well because it's a catalyst. So the Cl2 would not be there. So it's simply 2NO to form N2 and O2. And that would be the answer that you would put down here. All right. So what the final answer that I have from this part here, I'm going to put, you should put it down here. All right. Okay. Any questions about that one? Any questions?
I just want to make sure I'm right. Would it be 2NO reacts to give N2 plus O2, or N2 plus O2 reacts to give 2NO?
No, what you just said. 2NO, because 2NO is on the left side in the mechanism, and the O2 is on the right side, and the N2 is on the right side. So it's actually 2NO to give N2 plus O2. All right. Okay, so is it okay for me to get rid of this? Going once, going twice. Okay, so let me scroll down and let's see what's up next. Okay, what's up next is question number 10. Okay, so this is basically similar, I think, to an example I worked out in the video, and this is also in answer to a question that somebody asked earlier about the rate law not containing the intermediate, all right? So this question says, for the reaction, and it gives you the equation right here, show that the following proposed mechanism is consistent with the experimental rate law. So this is the experimental rate law, and this is a possible mechanism, all right? So what the question is asking for you to do is show that this mechanism here, when you work it out, should give you a rate law, which is this. And by the way, there's something missing. There's another typo here. Let me correct that right now. And the typo is that there should be a K right here. So please make a note of that, all right? So it should be rate is equal to K times the concentration of H2 times the concentration of NO squared, all right? So I'm going to need to, because I need space, I'm going to need to go to my writing application right here. So if you can download the assignment from Canvas so that you can have it to refer to while I'm going through this problem, make sure you do that now if you have not done that already, all right? Because I'm going to move away from this right here, all right? So the first thing I'm going to do is do this, do this, do that. Okay. Ooh, let me get rid of that there. Okay, so, all right, so the question says you're to write down or show that the mechanism is consistent with a particular rate law that has been established experimentally. So the first thing I would identify is the rate determining step. The rate determining step, I'm just going to rewrite it here. It's N2 plus O2 to give oh, I'm sorry. That's not it. What am I doing? I'm looking at something else. It's going to be N2O2 plus H2 to give H2O2 plus N2. So this is the slowest step. It's a rate determining step. And the rate constant for this step is K2, all right? So since the overall rate is equal to the rate of the slowest step, I'm going to write down that rate of the reaction will be equal to the rate of the second step, the slowest step, the rate determining step, which will be equal to K2 times the concentration of N2O2 times the concentration of H2, all right? Now you'll notice that in this particular equation, we have the intermediate appearing here. And in practice, we cannot determine directly the concentration of the intermediate, right? So that's why we try not to have it in the final equation for the rate law for the reaction. However, based on the first equation, right, we can establish a relationship between the N2O2 and NO, which is a reactant. So this is the second step in the mechanism. The first step in the mechanism is 2NO to form, and this is a reversible process, to form N2O2. Now the rate of the forward reaction is K1, and the rate of the reverse reaction is labeled K minus 1, right? So basically what we're going to assume is that this is an equilibrium state. And we're going to learn more about equilibrium later on, sometimes called a steady state. Basically what we're assuming is that the rate of the forward reaction will be equal to the rate of the reverse reaction, right? So the rate of the forward reaction would be equal to K1, concentration of NO squared, and the rate of the reverse reaction would be equal to K minus 1, concentration of N2O2, right? I'm sorry, this should be N, okay? So we can express this intermediate in terms of the reactant, right? All we have to do is divide both sides by K minus 1. And we're going to end up with the concentration of N2O2 is equal to K1 over K minus 1 times the concentration of NO squared. And then what we can do is that where this intermediate is present in this equation, we can plug in this entire expression where that is, right? So when we do that, you're going to end up with the rate of the reaction will be equal to K2 times K1 divided by K minus 1 times the concentration of NO squared times the concentration of H2, right? And if you look at this equation here carefully and compare it to the equation that was determined experimentally, you'll see that the only difference between these two is that where we have this collection of constants, that would be basically the same thing as K, right? So therefore we can say that, you know what, let me, since I need more space, let me erase the top part here. So basically we can say that the rate of the reaction is equal to K times the concentration of H2 times the concentration of NO squared, where K is equal to K2 times K1 over K minus 1. And therefore, the mechanism is indeed consistent with this rate law. All right. Okay. Any questions about this?
I had a quick question. When you wrote the concentration of NO2 or NO squared, why did you square that? I think that's like on the third line.
Because of, oh gosh, why is this not working? Okay, what's going on here? Oh, okay. Because of this 2 right here. You see that? So what I'm saying here, I think you're referring to this equation right here, right?
Correct.
Okay, so what I'm saying here is that the rate of the forward reaction in this step, which is K1 multiplied by NO squared, that's how I got this expression right here, is equal to the rate of the reverse reaction, which is K minus 1 N2O2, which is this right here. And again, let me emphasize is that we're making an assumption that this would be an equilibrium state achieved in that step, in step number 1. So I hope that answers it. I'm sorry?
If the coefficient was 3NO, would it be NO cubed then?
Exactly.
Okay.
Even though, as I said earlier, the likelihood of that happening is very, very small.
Okay.
It is very unlikely that you have 3 molecules coming together and reacting in an elementary step. But to answer your questions, at least theoretically, yes. If there was a coefficient of 3 in front of the NO, then you'd have to raise the concentration of NO to the 3rd pole.
Okay, thank you so much.
All right. Okay, any other questions about this particular question? Any other questions? Okay, so let me get out of this here and go back to the assignment. Okay, number 11. So this basically is just testing your understanding of different terms that is used in the area of chemical kinetics. So let's see if we can answer these questions together. All right. So the first question, the A part of number 11, says describe the differences between the following. And in the A part, it says catalyst and intermediate. So who'd like to take a stab at this one? What's the difference between a catalyst and an intermediate? Anybody? What's the difference between a catalyst and an intermediate?
A catalyst is produced at the end of the reaction and is a reactant at the beginning, and then an intermediate is produced by one step and then uses a reactant in later.
Okay. Okay, if it's a 4-point question, I'll probably take off half, only because the catalyst does not necessarily participate at the beginning, but it does participate earlier. You see what I'm saying? And then is reproduced later on. Not necessarily at the beginning, but earlier in the mechanism. So apart from that, you're correct. So I would say that the catalyst is involved early in the reaction, but produced later on, while the intermediate is the opposite. It's produced early on in the mechanism and then used up later on. All right. Okay. Now, speaking of catalysts, let me just talk about, before I move on to the other terms. I spent some time in the videos talking about some terms in relation to catalysts. Firstly, we talked about, if I remember correctly, the difference between a homogeneous catalyst and a heterogeneous catalyst, which is what question C or part C of question 11 is asking about, right? So let me see if you can tell me what's the difference between a homogeneous catalyst and a heterogeneous catalyst. Can anybody tell me? What's the difference between a homogeneous catalyst and a heterogeneous catalyst?
I feel like a homogeneous catalyst would be like the same exact molecule that is used.
Same something, but not same molecule. So you're partially right there. Same what? Anybody else?
Aren't the
Anybody else?
reactants in the catalyst dispersed in a single phase?
Exactly. So in a homogeneous catalyst is one that has the same phase as the reactants. All right. So if you understand that, then you should be able to tell me what the heterogeneous catalyst is.
They're found in different phases.
Exactly, right. The phase or the states of the catalyst would be different from that of the reactants, all right? So that's the difference between the homogeneous catalyst and the heterogeneous catalyst, all right? Okay, let's see if you guys can tell me, now that we have talked about that, because the B part is actually related to the heterogeneous catalyst that is mentioned in the C part. So B is asking for the difference between these two terms. One is absorption and the other one is adsorption. What's the difference between absorption and adsorption? Well,
In absorption, particles are absorbed into the something, and in adsorption, they just kind of are adhered to the surface.
okay. All right. Again, you're partially right. You're right about the adsorption part. When something is adsorbed onto something, basically the molecules of one substance is basically clinging or sticking to the surface of another substance, right? Now, absorption is when you have, and it's usually in reference to a liquid, when a liquid is being soaked up into a porous material, like a sponge or, something like that, all right? So that's the difference between adsorption and absorption. Adsorption is where you have molecules sticking to a surface of another substance, and absorption is when you have a liquid being soaked up into a porous material. And adsorption, going back to the first term, is very important when it comes to heterogeneous catalysts, right? And I'm quite sure I went into a discussion about examples of heterogeneous catalysis. I think the example that I did in the video is the reaction between, let me write this down here. If I remember correctly, the reaction is between ethene, also known as acetylene, and hydrogen. And this can be, hydrogen gas. This is a gas, by the way. Ethene is a gas, hydrogen is a gas. And the product of this reaction is a molecule known as ethane. And this reaction pretty much will not go unless there is a metal catalyst. The usual suspects are palladium, platinum, or nickel. All right. So clearly this is a heterogeneous catalytic reaction because the ethene and the hydrogen are gases, but these are metals, right? Obviously solids, and therefore these are heterogeneous catalysts in this reaction. And basically, if you look at the mechanism of this reaction, what is involved is that the hydrogen will cling to the surface of the metal. So this is your hydrogen, and there'll be a bond that is being formed between the hydrogen and the metal, and the result of that is the weakening of this bond. So you're going to end up with separate hydrogen atoms on the surface of the metal. We have some sites known as active sites. This is where the hydrogen atoms will end up being linked to, and then what will happen is that the hydrogen will move. Oh, and the same is actually going to be the case for the ethene molecule or the acetylene molecule. You're going to have the carbon atoms bonded to the metal surface as well, like this. And then what will happen is that the hydrogen atoms will move along the surface along with these atoms, the carbon atoms. And eventually what will happen is that the carbon will pick up a hydrogen in each case, and then the resulting molecule will be released from the surface of the catalyst, and you're going to end up with your product being formed. So that's basically what is occurring in most, I would say, heterogeneous catalytic reaction. And the actual applications of this, I'm quite sure you guys have heard of catalytic converters in the exhaust of motor vehicles. Basically, these are made up of special mixtures of metals known as alloys, which are designed to basically convert harmful exhaust fumes like carbon monoxide and other gases and convert them into less harmful products by allowing the reaction between these gases and oxygen. So in the case of carbon monoxide, it forms carbon dioxide, which is not as toxic, and other products as well will be formed as a result. And they basically operate on the same idea of the gases clinging to the surface of the material that makes up the catalytic converter, and that allows a reaction between those gases and oxygen, and you end up with your products being formed as a result. Okay, and these are very expensive parts of the motor vehicles, and I'm quite sure you have probably heard or read in the news that you have people going around actually stealing them from cars, going underneath the cars and cutting them out, and because apparently they're very expensive and they go for a lot of money. Okay, that's basically question The C, no, that's the B part. Okay, so let me clear this, do this, scroll down. Oh, okay, so the D part is asking for the difference between a first order reaction and a second order reaction. First order reaction and second order reaction. What's the difference between those two? Anybody? What's the difference between a first order reaction and a second order reaction? Hello, hello. We just talked about this earlier today.
A first order reaction involves one of the reactants, and the second order reaction involves two of the reactants.
Not quite. Not quite. Who'd like to help her out? What's the difference between a first order reaction and a second order reaction?
The difference between the magnitude of the way the rate increases when the reactants are increased?
Okay, that's partially correct. I would like something more specific, however. I'd probably give you half a credit for that answer.
Do you want an answer dealing with the reaction rates?
Okay, now we're getting somewhere. All right, so based on the rates of reaction in each case, what's the difference?
The first order
Mm-hmm.
is equal to the concentration of a reactant, and the other one is the concentration squared.
Okay, so repeat what you just said.
I said that the rate of the first order reaction is equal to, well, like the concentration of reactant over the change in time, but
Yeah, but what would that be? Yeah, what would be? I think what you're talking about is a rate law, right?
Yeah.
Okay, so what's a rate law for a first order reaction? Let's say the reactant is A, right? What would be the rate law for the first reaction, for the first order reaction? I'm sorry.
Rate equals K times concentration of A.
Okay, and then for the second order react, okay, so this is for the first order. And for the second order reaction, what would be the rate law?
Rate equals the K times the concentration of A squared.
Right, K times the concentration of A squared, right? So the obvious difference between them is the exponent here, or the power that the concentration of A is raised to. In this case, it's 1. In this case, it's 2, right? So the difference between a first order and a second order reaction is that in the case of the first order, the rate is directly proportional to the concentration of the reactant, A, right? Whereas in the second order reaction, the rate is directly proportional to the concentration of A squared. All right? So that's the difference between a first order reaction and a second order reaction. The rate of a first order reaction is directly proportional to the concentration of A, while in the case of a second order reaction, the rate is directly proportional to the concentration of the reactant A squared. All right? So that's basically how I would answer that question. All right? Any questions about that one? Any questions? Okay, what about E? I think E is the last part of question number 11. Yes, indeed. So in the case of E, they're asking for the difference between the average rate and the instantaneous rate. So what in your thinking, in your own words, is the difference between the average rate of a reaction and the instantaneous rate of a reaction? Anybody?
The average rate is the rate over a given time frame, but the instantaneous rate is the rate at a particular instant in time.
Perfect. Exactly. Exactly. That's exactly how I would word it. The average rate is the rate of the reaction over a time frame or time interval, while the instantaneous rate would be, as the name suggests, the rate of the reaction at a particular point in time or a particular instant. All right. That's basically the difference between those two. All right. Okay. Any questions about that? Do I need to say anything to further explain that? Okay, so that's basically it for this assignment. So now that we have completed assignment 10, what I'm going to do is, like I did for assignment 1, I am going to now create a Dropbox for assignment 2. So let me do that right now. And I'm going to require that this will be, okay, so today is the 5th. This will be due on the 7th, which is Friday at midnight. All right, so let me do this here. More options.
I have a question about the homework.
Mm-hmm.
And one of your announcements, it said something along the lines of having to put your name on each page.
Yes.
If we're able to upload it into one document, do we still have to do that?
Yes, please. And there's
Okay.
a reason for that, because sometimes the printer that I use here on campus, sometimes it acts up in the middle of me printing stuff. And therefore, as a result, I might have several pages of one particular assignment separated from each other. And therefore, it's very difficult for me to figure out, okay, what pages belong to one particular assignment. So that's the reason why I require, I'm sorry?
Is it okay if we just put our last name on each page?
Yeah, that will be fine, yeah. Last name, or even your ID number, anything that uniquely, that uniquely indicate that you're the person that submitted the assignment. Okay, let me just put some finishing touches to this thing here. 1, 0. Okay, so I have just created the Dropbox for assignment number 2. And, the same things I mentioned before, like what this young lady just mentioned, make sure that your name is at the top of each page of your assignment. Make sure it's completed in blue or black ink. If you do it in pencil, I can't guarantee that I'll be able to grade it, because sometimes the pencil writings come out real faint, all right? And I don't want to be struggling to read what you have written down. And what's the other thing too? And make sure that it is submitted as a PDF document, all right? That assignment will be due on Friday, all right? Okay, so let's, since we're finished now with the kinetics chapter, the next chapter that we're going to move on to is the chapter dealing with equilibrium. So let me go to Canvas. And, you know what? Let me remove this crap here first. And let me do this. I'm kind of surprised because that has never happened before. So I don't know what's going on with that. Okay, so any other questions before we move on to the next chapter? Okay, so the next chapter, as I said before, is dealing with a very important concept, equilibrium, chemical equilibrium. And we kind of touched on it earlier when we looked at one of the problems in the last assignment, but we're going to get into it in more detail here. Okay, so let me open this up. Okay, so let's talk about chemical equilibrium. All right, so let's talk about equilibrium, what it's all about. And basically, we're talking about situations where we have what is called a reversible reaction, all right? Hold on 1 minute. So if you have, well, firstly, let me say what a reversible reaction is. A reversible reaction is one that can go in both directions, right? And we saw an example of that later on, but let me use a simple example here. Let me get out of this here. And come on. Okay, let me do this here. Open this up. Okay, so I'm going to use a simple example. So let's say we have a reaction between hydrogen gas and oxygen gas to form H2O, right? So we can actually accomplish this reaction. It's very simple actually, but before I do that, let me balance this. So to balance this, I'm going to need a 2 here. I'm going to need a 2 here, and we have liquid water, right? So it's very easy to do this reaction, right? Basically, all you have to do is, if you have, let's say, a test tube filled with hydrogen, and you ignite it in the presence of oxygen, then you're going to hear a popping sound, which is an explosion actually, and water would be the product, right? But it is also possible for the reverse reaction to take place, right? Now, this one is more difficult to achieve. This can be achieved by carrying out a process called electrolysis, all right? All right, so basically this that I'm describing here is an example of a reversible reaction, right? Where you have 2 reactants, in this case, coming together to form a product, but you can also have the possibility of the product itself reacting to form back the original reactants, right? So that's basically what we mean by a reversible reaction, all right? And truth be told, pretty much all reactions are reversible, right? It's all a matter of altering conditions so as to favor one direction or the other, all right? So, that's basically what we mean by a reversible reaction. Now, in the context of the chapter that we're going to discuss today, we're going to talk about a lot, not only in this chapter, but the other 2 chapters following. We're going to talk about equilibrium, right? Now, what do we mean by this particular term, equilibrium, especially in the context of a chemical reaction? Well, a reaction system is said to achieve equilibrium where the rate of the forward reaction is equal to the rate of the reverse reaction, all right? So you can have both the forward reaction and the reverse reaction occurring simultaneously, right? But there's a special state known as the equilibrium state where the rate of the forward reaction is equal to the rate of the reverse reaction, all right? And another thing I need to say about this particular state of affairs is that this is describing what we call a dynamic equilibrium, all right? So we're saying that this is a dynamic equilibrium state where the rate of the forward reaction is equal to the rate of the reverse reaction, all right? Now, the key thing that you need to remember about this particular state of affairs is that even though you have the back and forth taking place, the concentrations of all the components, the concentration of all the components in the system will be constant. Right? As long as the system is in a state of dynamic equilibrium, the concentrations of every single item, every single substance involved will be constant. So for example, if this first example that I showed you here, if this was in a state of dynamic equilibrium, the rate of the forward reaction would be equal to the rate of the reverse reaction, but the amounts of H2, O2, and H2O will remain constant. That's basically how a equilibrium system works, all right? Okay, so now that I've shared that, let me go back to the PowerPoint here, and let me show you a diagram, actually a graph, which illustrates this whole concept, all right? So let me, hold on 1 minute. Okay, so as I said before, and as is stated right here, when a system reaches equilibrium, the rate of the forward reaction and the reverse reaction will be the same, right? So what this graph is showing you here is a plot of reaction rate versus time. Now, this line here, the green line here, represents the rate of formation of product as time progresses. And then this red line here represents the rate of disappearance of reactants. So as you can see, as the reaction proceeds, the amount of product the rate of formation of the product starts from 0 and steadily increases until it flattens out here. And then the opposite is true when it comes to the rate of reaction as far as the forward reaction is concerned, where the amount of reactant and the rate of disappearance of reactant decreases until it flattens out here. And you'll notice that they both are at the same level right here, and that's because it's in a state of dynamic equilibrium where the forward reaction rate and the reverse reaction rate are both one and the same. And as I mentioned before, after equilibrium, the concentration of both the reactants and the products will be constant, all right? So in this chapter, what we're mainly concerned about is what happens after this point right here, where equilibrium is achieved, all right? So that's basically what equilibrium is all about. Now, let's talk about, oh, you know what? Let me take a break here, and I'm going to restart at 1 o'clock, all right? So I'll be back at 1 o'clock. Okay, so let's finish up on this discussion right here. So let me go back to the PowerPoint. Okay, so we just talked about dynamic equilibrium, and I want to say more about this, and then we'll just call it today. Now, you might be wondering, how do we know that the equilibrium is dynamic? In other words, how do we know that there's a continuous back and forth occurring between reactants and products? Well, there are several experimental evidence which supports this idea. And here's one example. So let's say you start off with a saturated solution of sodium chloride. And this is a term that you should have met before, but just to remind you, when we say a solution is saturated, we are meaning that the solution has the highest amount of solute that can be present in it. If you try to add more solute to it, the extra solute will not dissolve. So that's what's happening here in the case of this saturated sodium chloride solution, and you have some solid sodium chloride down here. Now, the
We can't see
equilibrium.
your screen.
Oh, I'm sorry. I'm so sorry, folks. Okay, so let me restart quickly. All right, so as I was saying, so in this particular case, we have a saturated solution of sodium chloride, and we have sodium chloride solid right here, all right? So basically, what is believed to be happening in this particular situation is you have an equilibrium between the sodium chloride in the aqueous solution and the sodium chloride in the solid state, all right? So you have the back and forth taking place. Now, how do we know this? Well, if you add some sodium chloride, which contains radioactive sodium, right? Then what will happen is that, hold on, what's going on here? Hate when this happens. All right, let me just try to continue with this. So if you have radioactive sodium chloride, so let me put radio sodium, right? Chloride. It's actually the sodium that is radioactive, right? That would be in a solid state. So when you add it to the water, initially it's going to be in a solid state. Then eventually, if you wait a while, what will happen is that some of the radioactive sodium chloride will end up in the aqueous state, right? So what that tells us is that you have the conversion continually from the solid state to the aqueous state and back. And what you'll find is that the amount of sodium in the sodium chloride that's radioactive remains fairly constant, which goes back to what I said before, that the concentrations or the amounts of the different components in the system will remain constant at equilibrium, all right? So, oh shoot, okay, let me go back to this and let me erase this, or let me clear that. Go to this. Okay, so this is the radioactive sodium from the sodium chloride that is added here, and eventually some of that radioactive sodium will eventually makes its way into the aqueous solution. So this is evidence, and there are several other experiments that have shown this to be so. This is evidence that this equilibrium is not a static equilibrium situation. It's a dynamic equilibrium where you have the continual back and forth between the products and the reactants, all right? And just to illustrate again, this whole concept of equilibrium. So in this case, we have three different graphs here, and the equation for the reaction that is being demonstrated here is, okay, for some reason that is not working. So let me do this. Let me do this quickly. So the equation of the reaction that we're talking about here is HI reacting to form H2 plus I2, all right? So we're talking about this equilibrium system right here, all right? Now the first graph shows you what happens when you start off with 1 molar concentration of HI and no H2 or I2. What happens? The concentration of HI falls and then flattens out, and the concentration of both H2 and I2 would increase from 0 and then flatten out to this value right here, all right? So that's what happens when you start off with only 1.0 m of the HI and no H2 or I2 present. In this particular case, you're starting off with no HI, and you're starting off with 1 molar concentration of each of H2 and I2. And what happens in this case? The concentration of HI increases from 0 to 1.573, and the concentration of both H2 and I2 decreases from 1.0 to 0.213, all right? And then in the case of this situation where the concentrations of HI, H2, and I2 are all one that you're starting from here, what you'll find is that the concentration of HI will increase until it becomes a constant here, and the concentrations of H2 and I2 will decrease until it gets to a constant value right here. So in each of these cases, equilibrium is achieved. It doesn't matter if you start off with only H2 and I2, as in this case here, or if you start with only HI, as in experiment 1, or if you start off with a mixture of all three, right? In each of these cases, if you wait long enough, what you'll get to is a system that would have achieved dynamic equilibrium, where at that point onwards, the concentrations of everything, all the components, will be constant, right? So that's basically what happens as far as equilibrium systems being created are concerned, all right? Okay, let me clear this. Okay, so this is basically what you see here in the green boxes is basically what I just described. In each case, equilibrium is achieved, right? And this is basically showing you some data. And you know what? Come to think of it, what I'll do is stop right here, because this will take a lot more involved discussion, which I don't want to start and stop in the middle of. All right, so I'm just going to call it a day today for now. And we will meet on Monday. But let me remind you that assignment 1, if you have not turned it in yet, please do so by midnight tonight. Assignment 2, which we just completed, make sure you turn that in on Friday by midnight. And also, if you have not sent me a contact request for Skype, if you have not created a Skype account, please do so as well as soon as you can. All right. Okay, so that's it, folks.
I haven't
yes.
gotten a response back from you on Skype. Can you confirm whether you got my notification or not?
Let me see. This is who now? This is
McCoy.
McCoy. McCoy. Okay, I don't see. Let me.
It says on here waiting for Pete to accept the invitation.
Oh, so that means I haven't. Okay. Whoa, I don't see it here. You sure you sent it to the right address? Pete.nicely.
That's what I typed in, but it says the location is Clearwater.
Okay, so that should be me. So where is it here? I don't
I
see
sent it on Monday.
Let me type in your name here. Sometimes so you signed up as Alexandra McCoy?
No, my thing is A. McCoy 1996.
Okay, so maybe that's a problem. Let me see here. Is it one word?
Yes.
Is it MCCOY?
Yes. 1996.
1996. Okay. Yeah, you should have used your name.
Well, this apparently was an account created when I signed up for CF, and that was the name that was given.
Oh, okay. All right, so now I see it. So let me accept it. And let me make a record of it in my book here. Okay. Okay, thank you. So if you have not signed up, please do so as soon as you can. I see some people here signing up, so I'll get you guys recorded as being signed up. But if you have not done so yet, please do so ASAP. All right. Okay. Any other questions before I leave in the remaining 1 minute that we have left?
Yeah. Did you have any follow-up info about the testing locations up here?
No. I haven't had time to do that yet. In fact, I don't even think I'll be able to do it today, but I'm going to do it tomorrow. If not today, because today is my full day here in terms of teaching classes. But I'll get to it. No worries. I'll get to it.
Okay. And then will I will you send out emails or should I?
Yes,
just-
I'll, as soon as I know exactly, what to do, I'll message, those persons who won't be doing the test here, exactly what to do.
All right, thank you.
All right. Okay. So it's 1:10 now. Gotta go. So I'll see you guys on Monday. I'll be available, of course, for office hours on Friday from 12 to 5. So if you have any questions you want to ask me, especially in particular as it relates to the assignment, feel free to contact me via Skype during that time. All right. Okay. So until I see you Monday, take care. Enjoy your weekend.